Welcome to another episode of Terry's Notes, and today we are going to be looking at atomic structure. The word atom comes from the Greek meaning indivisible. Now, inside an atom we find the following particles. We find protons, neutrons and electrons. Neutrons and protons are found in the nucleus of an atom, and electrons orbit the nucleus of the atom. Electrons occupy specific shells or energy levels around the nucleus. Protons have a positive charge on them, and electrons have a negative charge. Neutrons are uncharged particles. The relative mass and relative charges of these subatomic particles are shown below. So the relative mass of a proton is 1. The relative mass of an electron is 1 over 1840. And the relative mass of a neutron is 1. The relative charge of a proton is +1. The relative charge of an electron is -1. And the relative charge on a neutron is 0. You need to be familiar with this table. Now, this diagram represents a simple structure of an atom. At the center of the atom is the nucleus, which is this part here. And what you will notice is that you have electron shells around the atom. So you have one electron shell here, we have 2, and we have 3 electron shells. These are the circles that you see around the nucleus. Now, the first shell can contain a maximum of 2 electrons. So you have 2 electrons in the first shell. The second shell can contain up to 8 electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8. And the third shell can also contain up to 8 electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8. Now, recall that within the nucleus we have protons and neutrons. We know that neutrons have no charge on them, but a proton has a positive charge. This means that the nucleus of an atom has a positive charge. The nucleus attracts electrons which are negatively charged around it. So this force between the nucleus and the electrons are what produces the centripetal force required to keep the electrons moving around the nucleus. The atom is electrically neutral because normally you have an equal amount of positive and negative charge. So therefore an atom is electrically neutral. Now, usually from the periodic table, when we represent an element, we see 2 numbers associated with it. The number at the top here represents the mass number, and the number at the bottom represents the atomic number. So for example, we have the element sodium, whose symbol is Na. So the sodium atom contains 11 protons, 11 electrons and 12 neutrons. Now, the number at the bottom is the atomic number. This will tell you how many electrons are present. So we have 11 electrons. It also tells you the amount of protons that we have. We have 11 protons because an atom is usually uncharged. Therefore, it must have equal number of protons and electrons. And in order to calculate the number of neutrons present in this atom, you will have to take 23 and subtract 11, and that is how we get 12 neutrons. Right? So, like I said, the atomic number is equal to the number of protons. The atomic number is also equal to the number of electrons. And the number of neutrons is equal to the mass number minus the atomic number. In this case, it was 23 minus 11, and we got 12. And you also need to be able to write what is called the electronic configuration of an element. So the electronic configuration basically tells you how the electrons are filled in the shells around the nucleus. Now remember, I said in the first shell the maximum amount of electrons you can have is 2. So therefore, if we write the electronic configuration, we start off by writing 2. In the second shell we can hold a maximum of 8 electrons, so it should be 8 for the second number, and this will give us 2 plus 8, which is 10. But remember, we have 11 electrons, so we still need to put 1 electron in the outer shell. So therefore the electronic configuration for sodium can be written as 281. Okay. The chemical properties of elements are determined by the number and arrangement of electrons in the atom. This table gives the electronic configuration of the first 20 elements of the periodic table. At the CSEC level, you need to be familiar with all of them. In this example, we have potassium. If we go back to the previous table, we know that potassium has atomic number 19. So we have 19 electrons. So how are they going to fill into the shells? In the first shell, we said it holds a maximum of 2 electrons, so we will have 2. So that's how we have 2 here. In the second shell, we can hold a maximum of 8 electrons, so it'll be 8 for the second number. In the third shell, we can also hold a maximum of 8 electrons, so we have another 8. So we have 8 and 8, 16, and 2, 18. But remember, the atomic number is 19. Therefore, in the outer shell, we will have 1 electron. So the electronic configuration of potassium is 2881. Now, we saw this in a previous slide. Usually, in the periodic table, you will see a symbol for an element. And at the top, we will have the mass number. We have the mass number here. And we will have the atomic number. And remember, I said that the atomic number tells you how many electrons and how many protons are present. And the difference between the mass number and atomic number gives you the number of neutrons. So the atomic number is the number of protons in the nucleus of one atom of an element, and the mass number is the total number of protons and neutrons in the nucleus of an atom of an element. So you need to know these two definitions for atomic number and mass number. Now we will look at something called an isotope. Isotopes are atoms of the same element with the same number of protons and electrons but different number of neutrons. So what we are saying is that they have the same atomic number but different mass number. And remember, earlier I said that the atomic number or the number of electrons are what determine the chemical properties of an element. So therefore, if isotopes have the same atomic number but different mass number, we expect them to have similar chemical properties but different physical properties. An example of isotopes of chlorine, we have chlorine 35 and chlorine 37. And this is how we represent the two isotopes. Both of them have the same atomic number of 17. But if you notice, their mass numbers are different. One is 35 and one is 37. Therefore, for chlorine 35, it will have 17 protons, 17 electrons, and it will have 35 minus 17, which is 18 neutrons. In the case of the chlorine 37, it will have 17 protons, 17 electrons, and the number of neutrons will be 37 minus 17, which will give us 20. So if we look at the two isotopes, we realize they have the same number of protons and electrons, but the number of neutrons are different. The next thing we need to look at is radioisotopes. Sometimes atoms of isotopes are unstable. They spontaneously split into smaller atoms and release energy in the process. This energy is called radiation, and the unstable isotope is called a radioisotope. Now, there are three types of radiation. We have alpha particles, beta particles, and gamma rays. In the case of an alpha and beta are particles, and gamma radiation is an electromagnetic wave. An alpha particle is simply a helium nuclei with a +2 charge. A beta particle is a fast-moving electron with a charge of -1. And a gamma ray is a high-energy electromagnetic radiation. It has no charge. So you need to be able to tell the differences between these three particles. So the alpha particle is just a helium nuclei, the beta particle is a fast-moving electron, and a gamma ray is just high-energy electromagnetic radiation. Uses of radioisotopes. Now, cobalt-60 is used in cancer treatment. In a cancer patient, we usually have an uncontrolled growth of cells, and what the cobalt-60 does is it produces energy that kills the cancer cells. Radioisotopes are also used as tracers in living systems. For example, iodine-131 is used as a tracer to check the functioning of the thyroid in humans. Carbon-14 is used in the study of photosynthesis in plants. Plutonium-238 is used as an energy source in heart pacemakers. A pacemaker is a replacement heart that is used in the human body. So the plutonium-238 provides the energy to power this pacemaker. Carbon-14 is used in the dating of plants and animal remains. And the last use is in the production of electricity. Uranium-235 is used in the production of energy in nuclear power plants. Now, let us look at an example here. The relative atomic mass is the average mass of one atom of an element compared to the mass of one atom of carbon-12, the mass of which is taken to be exactly 12.00 units. Now, in the earlier example, we know that chlorine has two isotopes, chlorine-35 and chlorine-37. Naturally, they occur in a ratio of 75% to 25%. And the question is, what is the relative atomic mass of chlorine? In order to calculate the relative atomic mass of chlorine, we need to take the percentage, which is 75%. So it'll be 75 over 100 multiplied by its chlorine-35 plus 25%, that is 25 over 100 multiplied by 37. And when we calculate this, we get 35.5. That is why in the periodic table, you will see chlorine often written as 35.5 and 17. This is where they got the 35.5 from. Naturally occurring chlorine consists of chlorine-35 and chlorine-37 in a ratio of 75% to 25%.